Alright, hello Justin. Today I'm going to be presenting the molecular geometry and bonding for the molecule HCCH3. To start off with, we know we got 4 hydrogens and 3 carbons. And knowing with that information, we got to know the valence electrons from both of these elements. So to reference the periodic table, starting off with hydrogen, we have 4 hydrogens, and this hydrogen is going to be in group 1, and therefore has 1 valence electron. So we do 1 times 4, 4 valence electrons, we have 4 hydrogen. And then moving along for carbon, we have 3 carbons. And then we look at carbon here, it's at group 4, therefore it has 4 valence electrons. 4 times 3, 12 valence electrons. Add the valence electrons, the 12 from the carbon, 4 from hydrogen, to determine 16 valence electrons. And then moving along, after knowing the total amount of valence electrons we're going to use for our Lewis dot structure, we need to determine what's going to be the central atom. In this case, it will be carbon, due to the fact that hydrogen cannot achieve the octet rule due to only needing 2 electrons to reach a noble gas configuration. Meanwhile, carbon follows the octet rule by either losing 4 electrons or gaining 4 electrons. In addition, carbon will also be the least electronegative element in this molecule. Alright, and here's the Lewis dot structure. We got all the 3 carbons in the central of the atom, while hydrogen is going to be outside of the carbons. And since we use 16 valence electrons, we can verify that we use all 16 of them. Alright, and we know for sure that one bond is going to be 2 valence electrons. So 2, 4, 6, 8, 10, 12, 14, 16. Alright, that works out. And now we got to make sure we followed. And now I'm going to make sure that my formal charge equals to 0 to make sure that this is the Lewis dot structure at a stable state. So hydrogen has 1, that works out. Hydrogen 1, that works out. Hydrogen 1, hydrogen 1, all good. And then carbon needs 4, so 1, 2, 3, 4. Yep. Second carbon, 1, 2, 3, 4, works out. Third carbon, and then 1, 2, 3, 4. All right, so since my formal charge were all 0 for all these elements, then it's at its current state. It's the most stable state at the moment. And having my Lewis dot structure all checked with the most stable state, now I can move on towards sigma and pi bonds, which is applicable to the central atoms. So to begin with the left carbon, I'm going to have a sigma, 1, 2, 3 sigma, and then with 1 pi bond. For the middle carbon, I'm going to have 1, 2 sigma and 1, 2 pi bond. For the third carbon here, I'm going to have 1, 2, 3 sigma bonds, and then 1 pi bond. Alright, and then my lab partner, Chris, is going to reference my number of sigma pi bonds for these carbons to determine the hybridization, bond angles, and molecular geometry.
Hey, what up, guys? I'm pretty sure my man Frank already explained to you the functions of this Lewis structure and how it's formed like this. So today I'm about to learn you these tables right here and how to fill them up. We're here to discuss the hybrid orbital, number of sigma and pi bonds, molecular geometry, and bond angles of the various carbons that are found in this chemical. We don't count the hydrogen because hydrogens are, or we don't include those. For the hybrid orbital of the first one, remember that in order to find the hybrid orbital, you need to find the number of electron domains in each chemical. So in this case, for each not chemical element. So in this case, the first carbon has 1, 2, 3, 4 electron domains, so that automatically gives it hybrid orbital of sp3. Um, Keep in mind that as the number of electron domains increases, in terms from like if it has two electron domains, it has a hybridization of sp. If it has three, it has an hybridization of sp2, and if it has four, it has a hybridization of sp3, in which we use that example. For number 5, it turns into sp3 plus, and so on and so forth. Um, so next is the number of sigma and pi bonds. So in order to find this is actually really really simple. Um, so keep in mind that we're here to count the single bonds, the double bonds, and the triple bonds, or to find these sigma and pi bonds. So um, keep in mind these rules that for every single bond and double bond and triple bond, there is I'm gonna tell you how much sigma and pi bonds there are. So there is let's just write it down. So for every single bond there is one sigma and 0 pi bonds. For every double bond it has for the double bond it's 1 sigma and 1 pi bond, and for triple bond it's 1 sigma and 2 pi bonds. You can see like only the pi bonds increases for every single added bond in the structure. So in this case the number of sigma and pi bonds for this one is, let's count the electron domains associated with this element. So it's 1 2 3 4 single bonds, which means it has 4 sigma bonds, and as you can see there's no double or triple bond surrounding it, so it's 0 pi bonds. So next is the molecular geometry of this carbon. So keep in mind that the molecular geometry varies with the number of lone pairs that each element has in the structure, which in this case there's no lone pairs, so that automatically gives us the idea that the molecular geometry of the first carbon is tetrahedral. And with tetrahedral gives us a bond angle of 100 and 109.5. And now let's move on to the second and third carbons, in which I already discussed these rules, so we should be getting into them pretty quickly. For the hybrid orbital of this, um, uh, you can see that for the second one we have a triple bond in this second carbon. So as you can see there's no extra valence electrons around it, so that makes it so the lines here indicates that it has 4 electron domains, same as the first one, so its hybrid orbital is going to be sp3. Now next is the number of sigma and pi bonds. As you can notice, as I discussed earlier, this already has a triple bond and a single bond. So a triple bond means, if we would look at these rules above that I wrote, one triple bond is equal to 1 sigma bond, one sigma bond, and 2 pi bonds. So let's count our bonds. So it's one single bond and one triple bond. So that automatically makes it one single bond, one plus one triple bond, which is two. So it's two sigma bonds and two pi bonds because it has a triple bond. The molecular geometry of this one is so let's see, there is no lone pairs anywhere basically in this structure. So that automatically gives us the idea that well, it's the same as the first one. So if it has zero lone pairs and it has four electron domains, its molecular geometry automatically tetrahedral with the same bond angle of 109.5 degrees. Now the final one, as you want to see, like the final one kind of looks like the second one, in which as you can see, I mean, there's no lone pairs, no extra valence electrons. So as you can see, it's pretty much the same as the second one. So hybrid orbital, it's like 1, 2, 3, 4, 4. So that gives it as a hybrid orbital sp3. It has one triple bond and one single bond like the second one, so that gives us 1 plus 1, 2 sigma bonds, and 2 pi bonds. Now there's no lone pairs in this one, so that gives us a molecular geometry of tetrahedral with a bond angle of 109.5 degrees. As you can see, as you cannot see because my lights turned off, oh, wait, oops. As you can see,